I guess my login had just timed out when I first started doing it here a moment ago. We may have other students that jump into the class throughout the day by way of the link here on YouTube, and they will actually give us a. Okay, let me. There it is. Okay. So, like I say, we may have other students that join us throughout the day when they go to our website, see the link on YouTube, and our webmaster Keith will provide me with a link to the YouTube channel where you can, and I'll actually send it to you all so you can go back and review the recording later on, this evening if you wish. They don't do that often, and they don't allow the students to actually record it. But when we do the broadcast on YouTube, I can provide you that link where you can look at it later. Now, we touched yesterday briefly, didn't go over it in much detail. We touched briefly on some of the networking hardware. I mentioned routers and switches and hubs and things like that. We'll take a look at some of this hardware in a little bit more detail. I'll give you an overview of the different network types from the smaller personal area networks all the way up to the large, very large area wide metropolitan area networks, they call those. Networks are basically broken down and always begin with what's called a LAN or a local area network. Local area network is typically, not always, but typically located in a single location, like in an office building or on a campus, for instance, and sometimes like in the like in academia where they have multiple buildings, multiple locations on the same campus. Even those being spread out, they're still basically in the same geographical location. And those systems are more often than not typically tied together, either hardwired or wireless. Typically, hybrid combinations of wired and wireless make up those networks. Then we get into large geographic locations, and there's several different versions of these networks. They're called wide area networks. And that's if you have, for instance, a home office, multiple branch offices that are communicating together. They're typically made up of LANs or local area networks in a singular location or multiple locations, home office, branch offices, things like that. And then those are communicating together um, more often than not using the internet as the main communication vehicle. But that constitutes what's called a WAN or a wide area network. There are hybrid type of networks or the common beast out there, where it is a combination of hardwired connections and wireless connections. And then there are wide area networks or local area networks that are wireless only. WLANs, they call the local area networks that are completely wireless. There is an organization known as it's IEEE, the Institute of Electrical and Electronics Engineers, and they publish guidelines and standards. They are a think tank, so to speak. They work real closely hand in hand and have for years with another acronym organization, the Internet Engineering Task Force, IETF. There are also another couple of institutions and organizations, the IEA, the I'm sorry, the TIA is the Telecommunications Industry Association, and then the EIA, the Electronics Industry Alliance. They also publish guidelines and standards, and the EIA TIA combination were the ones that originally came up and standardized the wiring. When we'll look at later on the wiring standards for Ethernet cabling and telephone cabling and color coding, things like that. The IEEE also publishes standards that are guidelines for implementing wired networks, and those standards are referred to as 802.3. The wireless standards, as you see here, published are called 802.11, and that guideline and standard identifies, for instance, the wireless access point versions that were created in order to provide wireless networking. There's 802.11a, 802.11b, 802.11g, and they're on up in the high order now, 802.11ax and az. And it just defines the different attributes, properties, and characteristics, speed, frequencies that the wireless networks utilize, and so on within those different standards. When you start putting together these large geographic areas and tying all of these wired and wireless local area networks together, then those constitute a couple of other terms, which we have here. The metropolitan area network is one such. In the greater Atlanta area, we have a large metropolitan area network here, which incorporates mostly government offices, but it also spans over about 4 different counties, including Fulton County, where it is the city of Atlanta is housed, and several surrounding counties there as well. You guys probably aware, the greater Atlanta area, we have an interstate system that circumnavigates the city, Interstate 285, and closely following that ring around the city is a couple of very high-speed fiber optic networks, fiber optic connect points. And then you have these multiple county governments as well as the Atlanta city governments attaching their systems to that, and they all intercommunicate quite nicely. When you break the networking down to a personal side, we have, for instance, your mobile phone and your earbuds, or mobile phones and little speakers. That's called a PAN, a personal area network. So very small types of connectivity, doesn't cover a large area as far as networking is concerned. And then there's another network that we see used a lot, as a matter of fact, for cloud-based storage and in large data centers as well. It's called a SAN, an SAN, a storage area network. And the entire network is dedicated to providing storage capacity for many different computer systems. There is a scaled down version of a local area network. It's called SOHO, Small Office Home Office. And most of us have these types of SOHO networks in our homes. I have one here. I've got my router gateway device here. Now I chose not to lease the one from the network provider. I bought my own, but it serves the same purpose as the one that, if they lease it from your internet service provider. Some of them look very similar to this. The newer ones now don't have the antenna exposed on the outside, many of them. And the one that we have here is it's fiber optic cable right into the router. So very high speed. And then mine has 6 external communication ports on it as well. And so part of my network here is hardwired. Part of the network is wireless connectivity, much like this diagram here. And then you have some type of very high-speed connection. It's either coax or fiber optic cabling now, for the most part in large areas, right out to the internet, the World Wide Web. And then all over the globe, there are these basically these termination points, these large network termination points. They call them IXPs, Internet Exchange Points. And then within those IXPs, super large data centers, thousands and thousands and thousands of cables of every kind you could imagine that terminate into this large data center. And that's also where you'll have all of your internet service providers, the ISPs, like Comcast and Verizon and AT&T and all of the other providers all across the world. That's where they will have their large routing and switching equipment housed inside of those IXPs. And then they're the ones that provide you the access to the internet, the World Wide Web. If you go into larger, medium and large size enterprises, just take this view right here and expand it 100-fold, rather than supporting 5, 10, maybe 15 devices. They may be supporting 250, 300, 500 devices. And once again, combinations of wireless and wired appliances. And those appliances may be laptop computers, desktop computers, mobile phones, all types of communication devices, all of which have some type of computing capability. This is a pretty good diagram here, I tell you, that defines a very standardized enterprise-wide network. When I was doing networking, I always like to set up my networks in these broken down work areas, subnet areas, and isolate those typically departmentally or divisionally. It's not required, but it just gives you a better means or an easier means of actually managing all of the individual subnet areas inside your network. Now we have these large, very high speed switches. Some of the switches that are manufactured are 10 gigabits, 20 gigabits, 30, 40 gigabits per second as far as the speed. And the really high speed ones are, they call them core or distribution switches. Um, and we're also seeing quite the convergence now, and I think we're going to see more of it, of functionality, whereas you used to have completely separated router device, firewall devices, switch devices, hub type of devices. We're now beginning to see lots of organizations are beginning to aggregate those into a singular appliance. My router that I have here in my home network, many of you as well. It's the router, it's the gateway device, it is the firewall, it's the switch, all composited into a singular appliance. So that's a pretty good deployment model here, and graphic as to how enterprise, small, medium, and large type enterprise networks are laid out. Here you got the wireless access point here, where all of these wireless devices here are communicating to this wireless access point, and then it is hardwired usually from the wireless access point into one of the switches, the work group switches. And then those low speed switches, 10, 20 gigabits per second, are then piped into, usually with redundant paths, to multiple larger core switch type devices. And then all of that composite data is then handed off to your what they call perimeter routers. And then the router does several different functions. It makes the determination, are you wanting to communicate internal inside of your autonomous network, or do you wish to communicate outside over the public internet? And the router, the gateway function of the router, makes that decision. We'll get into that more later in our current IP scheme, the IP version 4. The gateway device uses what's called a subnet mask, and then it compares your IP address with the IP address you want to send to determine first, are you inside the same network? And if you are, it will just bump it back, usually back into a switch device and move that data inside your network. Or if you're wanting to communicate outside of your network, even into a different subnet within your own network, well, it routes that data accordingly to the proper device that then moves it on to the individual workstation you're trying to communicate with. So the router gateway device does lots of heavy lifting inside of networks and makes lots of very rapid decisions as well. Inside of corporate data centers are typically designed to house your high-speed switching appliances. That might be in a wiring closet somewhere. It may be separated in an area in the data center. That's where you have your server class machines, typically, application servers that are going to be serving up print jobs, handling, managing print job functions. You'll have more often than not some data storage component inside the data center. Sometimes those are on site, sometimes they're off site, cloud based access to data centers. But the data centers themselves are typically housed inside of a relatively secure environment, should be very secure. They also have, all the power facilities that can supply power for all of the big machinery. They're usually housed inside of a tightly climate controlled environment. Of course, computer systems generate a lot of heat, so they have to have a lot of cooling in the data centers there. So the data centers, that's also where, and oftentimes your networking wiring components terminate inside the data center. So that's where they also may have your networking hardware, including your switches, your routers, your hubs, things like that. It's all according to how the enterprise actually sets it up. Now, I mentioned to you guys yesterday, and I gave you an example of this MAC address, this hardware address. Media Access Control is that acronym, MAC. It is a 48-bit hexadecimal address, and it actually appears as 6 different hexadecimal characters. Hexadecimal characters made up of 2 digits or 2 characters. And what I showed you yesterday, A1, 00, 18, 1C, those kind of things. Those are all hexadecimal digits. Now, hexadecimal, as you guys should know, is a base 16 numeric system. It includes the digits 0 through 9 and the alphabetic characters A, B, C, D, E, and F. Those alphabetic characters also have underlying numeric values associated with them, and it's 10, 11, 12, 13, 14, 15. Okay. So a total of 16 available characters in hexadecimal. One of the things you might get on your exam, they'll show you a listing of different what looks like MAC addresses, and they'll ask you which of the following is a valid MAC address. Well, if they have something down there that one of the characters is H15 or one of the characters is 1N, well, those are invalid because the only valid characters in hexadecimal are 0 through 9 and A through F, period. Anything other than that is not a valid hexadecimal character. Okay. The MAC address never changes. As I gave you the example yesterday, it is hardwired into the network interface card, the NIC, the network adapter. You can use a program tool. This one is it's called Wireshark. Give you guys a link to the Wireshark utility right quick. Oh, and don't forget to, if you haven't already done so, guys, grab those files from the wormhole site. It will be expiring here in just a little while. The Wireshark tool is, in my opinion, an excellent program. It is free, completely open source. I have it running on, I guess, all of my PCs. You should download it. What it allows me to do is to capture data packets as they flow on a network between computer systems, wired, wireless. Wired is an example here where I've captured the data frames that flow between 2 computer systems during a communication session. Now, people tend to think that computers have this just constant stream of information that flows from one system to another system. That's not at all the case in an IP network. What the computer systems do is it takes this, say, well, like we're communicating here with the audio and the video being output from my location. It appears that it is just one constant stream of information, when indeed the video and audio broadcast is broken up into very small, digestible, what they call frames or chunks. And then it flows across an IP network between me and the Zoom servers. And then when you guys attach with your Zoom package, it pulls that off of that server in the stream. But again, it is still packets of data. Those packets of data are sent oftentimes different paths according to how the routers move them through the internet, through the network. And sometimes they arrive out of sequence. So each individual data frame or packet has a sequence number associated with it. So when all of the frames are when the frames are received on the target side, it will reorder those so that it's all in the right order, and then push it out to the Zoom player so that you can play it back. I can look at each and every one of those data frames and capture those with a tool like Wireshark. And it tells me some valuable information. It tells me the from address, the to address, IP address typically. Sometimes it's the just the MAC address if it's local. It doesn't hide the MAC address. All the MAC addresses are revealed down here in the detail. Any of the items that I click on up in the top of the page, it updates the detail here and then down at the bottom of the page as well. This is the binary equivalent of information up here that has been captured by the Wireshark tool. Now, in the Network Plus class and several of the other classes after this one, we get a lot more detailed in the use of the Wireshark tool. And it's a great tool that I think every network engineer should be very, very familiar with on how to use, because I can look at the raw data on each frame that is being broadcast. And it shows me things like what's in the data frame, what's in the packet, the sending address, the receiving address, the type of software or protocol that's used to transmit and structure the packet. All of that I can see with that
I have a
Wireshark tool.
question, sir.
Yes, ma'am. Go ahead.
So isn't some of the packets encrypted though to where you can't read them?
Some of the data frames and packets are indeed encrypted, but there's certain things about it. For instance, the MAC address that is exposed in the header of the packet, so you still read that. Now, the data, the actual data payload that is there, whatever the data happens to be, you can see it, but if indeed it's encrypted, you won't be able to make any sense of what's in there. It'll just show up as, other data chunks down here and not clear text data. Very good question, yes. But there are certain things about the data frame that encryption doesn't hide, the MAC
So
address being one of those,
if you had a VPN,
right?
then would it be encrypted the MAC address and like IP address?
Well,
Or would you not be able to see those?
with a VPN, I wouldn't even be able to see these data packets to
Okay.
capture those with a tool like Wireshark.
Oh, okay.
Yeah, that VPN, that's some pretty interesting stuff. It's like having three wrappers of encapsulation around your data frame, so you can't even get to it and pull the information.
Okay.
And I'm very glad that you thought about the VPN, because, in my humble opinion, you should never go onto a public network without firing up a virtual private network client for sure. So, very good question, Kaylee. Thank you, ma'am, for that. I appreciate it. Now, this is the what looks like the back panel as you would go into a wiring closet. And there's a very specialized tool. We'll look at the tool later on. It's called a punch down tool that I use to strip back all of the wires and punch them right down into what they call these keystone jacks. The wires are color coded. They need to go in very specific order in the jacks there. But this is set. These don't change. Now, on the front side of the patch panel, it looks like this. You have your individual ports. Those are nowadays they're a combination of these guys, which is the RJ45 port, which is the 8-wire twisted pair. People call it Ethernet cable. Ethernet is actually the method that's used to transmit the data, but it's still known as Ethernet cabling. And you'll see down here, this little guy right here, that's your regular RJ11 telephone cable plug. They can be accommodated in most of these patch panels as well. Um, can either of you tell me, looking at this patch panel here, now it's very well managed with these cable holders here, but what is missing from this photo? And this just drives me crazy when I go in and look at a wiring closet and don't see it. What's missing there? It's the labels. They've got the patch panel itself labeled, but let's say a disgruntled employee on the way out the door just went into this wiring closet and unplugged all those wires. Where do they, how do you plug them back in? I want to see labels around the ends of the cables, and those labels should coincide with wherever the other end of that cable is plugged into a wall panel or a cube space or not, whatever. So, yes, I want the labels on the patch panel itself, but I want the cables labeled as well. Okay. So managed well. I like the way they manage it with the hooks there, and everything looks nice and orderly. But like I say, if somebody comes in there and just disconnects all those cables, what do you do? Switches are a little bit different beast. A switch is a device that looks like this right here. Okay. Now, the new switches are much more intelligent than the old passive switches. The old passive switches were basically called a hub or a bridge. They didn't do a lot of intelligent processing. It was just a singular hub was what was called a large broadcast domain, because everybody that was plugged into the hub, if they broadcast a message, even though it may be meant for the user that's on port number 3, that message was broadcast to every one of the ports, and each individual user had to make the determination on each broadcast, is that meant for me? And if it is, I'll process it and respond. But if it's not meant for me, I just ignore it. So everybody was vying for the same communication capability, and every message was broadcast to every port on the switch. These newer managed multi-layer switches manage that much more efficiently. They create inside of the switch itself. Go back to the slide here. It gives you the name, the CAM table, the Content Access Management Table. And the table looks similar to this right here. It says, all right, for port 1, here's the MAC address of the computer that's plugged into port 1. Here's the MAC address of the computer that's plugged into port 15. So if I'm the computer in port 15 and I want to talk to the computer that's in port 1, I don't broadcast that message to every port on the switch. It broadcasts it into the switch. The switch looks at the CAM table there and says, oh, okay, the computer you're wanting to talk to is plugged into port 3. So then it establishes a direct port-to-port communication between me and the computer in port number 3. Okay? And the modern switches too also give us the ability of establishing simultaneous full duplex communication. They call it. Uses multiple data channels so that we can send and receive data simultaneously. Okay? But it doesn't broadcast that to every port on the switch. The table knows where all the computers are plugged in, what their MAC addresses are, and it manages that communication much more efficiently than the old broadcast domain did. Okay. So, even with the switches as well, I can do another cool little thing. I can create what's called virtual local area networks inside of the switch itself. Okay. Now, in the old hub devices, the unmanaged switch, you just plugged it in and went. Actually, I've got a 5-port switch here sitting on our hub, sitting on my desktop, which accommodates my big screen TV, the other big screen monitor I have here, and both of my laptops are hardwired into my router, which sits down in the great room. And they're all plugged into this hub device. And then I have one Ethernet cable that goes down and plugs into the router downstairs. So they're all sharing that particular hub link. And it's not managed. It's the old hub type device.
Sure.
Now, the managed ones, they have a control language down under the covers inside the switch itself. And some of them are starting to try to give you a graphic user interface, web-based looking interface that you can manage the thing with, or you can get down into the switch command language itself and do the configuration there as well. Some of these things, the largest one I've ever worked with personally had 48 ports on it. And with the command language, I could also create these further subdivisions on the switch called virtual local area networks. Now, that's a subject for a completely different class, but I'll mention it and give you some more detail on it later on. These switches, typically now we see those that are enclosed in these large 19-inch racks inside server rooms, and they all communicate together. Yes, Kaylee, go ahead.
So how do the switches know which computer goes to what port? How
Well,
does that
okay,
set up?
good. Yeah, good question. When you plug it in, your computer, the switch says, what is your MAC address? And the computer then presents that MAC address to the switch, And the MAC address says, I mean, the switch says, okay, you just plugged into port 18. Here's your MAC address. I'm putting it in my table. So
Oh,
just the fact that you plug a computer into that port, it offers up the MAC address.
so I'm just trying to visualize in my head. Is the computer plugged directly into the switch, or is it plugged into something that
Typically,
travels to this?
typically the computer is plugged directly into the switch. Let me go back and show you this configuration we looked at here earlier. Okay, where was it? Oh, I got to back up a little further. Oh, hold on. This guy right here. Typically, the computer systems are either plugged into a patch panel of sorts. Now, more and more, we're seeing rather than this patch panel like this, the switches are moved and take the place of that patch panel like so. So the computers then are plugged directly into the switch. Okay. Like this situation here. Here's the switch. So you got these two server class machines, this printer plugged directly into the switch. Same thing over here. All of these guys, they are in this case, they're plugged into the wireless access point, or they're communicating. And when they communicate with the wireless access point, they also offer up their MAC address to this guy so it can track them as well. So more often than not, the computers are plugged straight into these switches,
Can it
and
be
the switch
wireless?
not well, yes, well, it is wireless because the wireless access points themselves also play the role of a switch. So it tracks the MAC addresses on those guys as well. So conceptually, same thing as this right here, only in the wireless realm. Okay. Or I may have a wireless access point with a bunch of wireless devices talking to it, and then a singular connection to a switch, but all of their MAC addresses flow over that same link there too, so it can manage them as well. It knows where they are. Yeah. Yeah, I tell you, these switches and good questions as well. These switches and the router functionality and the gateway device, they're all being converged and playing these multiple roles here in this very intelligent device here. But that's to answer the first question. When you plug a computer in, it offers up and says, "Here's my MAC address," and the switch says, "All right, I'll put you in the table. You're attached to port number 3 or port number 5." So we see these downline or work group level switches that are typically oriented and have all the cabling coming in from the different departments or divisions or work groups. And then they are hardwired all the way up to what they call TOR switches, top of rack switches here. And these are the really super duper high speed ones. Those are the ones I was talking about in the graphic earlier that were the core of the distribution switches. So all of these switches pipe their connections up to these guys, and then these guys then communicate out to your very high speed router devices that typically sit on the network perimeter, and that provides them the ability of routing traffic out, usually over the public internet, to other network connections out there. So very modular by design. These are usually the 19-inch rack mount modules that go in server type rooms there. Okay. Now this is a sort of a listing there of what down under the covers when you're looking at the switch language. It gives you information about all of the traffic that's flowing back and forth from port to port, computer to computer, upline, downline in the switch. You can go in and configure the some of the characteristics of the switch. And like I say, these things come in different speeds, 10 gigabits per second, 20, 30, 40 gigabits per second. We're also seeing Cisco and a couple of the other vendors now are beginning to experiment with some really super high speed switches, which I think we're going to see coming down the pike here in the not too distant future. This is a cool little concept here, and you guys may have seen an implementation of this. If you've seen the security systems like where you have the, the device that actually records video cameras for security cameras. And then they have cameras that, for instance, putting them on four corners of a building, for security implementation. This power over Ethernet standard here, or standards, provide the ability so that you don't have to run an additional power cable from the switch device out to the camera itself. The power can be sent right down the 8-wire twisted pair Ethernet cable. And I mean, heavy duty power too. You can, some of them, they're experimenting now with up to 70, 75 watts of power right down that same network cable. So you don't have to run additional power cables. Now, the switch has to be PoE enabled. They call it power over Ethernet enabled. And there are different versions and layers of which, of course, offer you different speeds. There's a 802.3AF, which is the first type 1 power over Ethernet. It will deliver consistently up to 13 watts of power. It can deliver 15 watts, but it's consistently up to 13. PoE Plus, or Type 2, is higher than that. It will deliver all the way up to 30 watts of power, but they guarantee, and it's consistently about 23 to 25. And then the super high speed ones there, those things are beginning to push the envelope there, Type 3 and Type 4, of 40, 45, 50, 60, 70 watts down the wire. Now that is wattage at 48 volts, but still plenty of power to drive small display screens, pan, tilt, zoom cameras, very, clear video quality cameras. But again, the switch has to be able to support that because it's what provides the power. And there are, if the cabling that you're sending it down is longer than about 100 meters, that's usually the limit on Ethernet cabling, Cat 5, Cat 6, Cat 7 Ethernet cabling. If it needs to go longer than that, you may have to put inline, basically power boosters or injectors, they call them, in order to send that signaling on down the line there. But a very, very slick device. Good buddy of mine worked with when they were building the Mercedes-Benz Stadium here in the greater Atlanta area. He's a networking guy, and he was telling me that they put in, he said, about 1,000 miles of Ethernet cabling, and all around internal inside the stadium, they've got these little tiny display screens and these very sophisticated security cameras. He said it was all driven on the power over Ethernet stuff. So, we started talking about the network interface cards. You looked at the NIC yesterday. That is the component that has the physical MAC address associated with it. We talked about the managed or multi-layer switches as opposed to the unmanaged hubs. And we talked about power over Ethernet there. Now we start getting into your specific configuration of your network cables. This is the old trusty 8-wire twisted pair. Color coding is very specific. You have 4 pairs of twisted conductors. You have a solid orange wire with an orange and white striped wire twisted tightly together. You have a solid green and a green and white striped wire. You have a solid blue and a blue and white striped set. And you have a solid brown and a brown and white striped set, tightly twisted together. Now, the recommendations on the twisting vary based on who you're talking to. But usually it's about 12 twists per inch. And the twisting serves a purpose. It is designed there to cast off what they call alien crosstalk. So it sort of acts like a filter to keep the traffic flow down any of the other wires from invading the signaling wires, the transmit and receive wires. The TX, RX transmit receive wires are the orange and the green twisted pair, by the way. The cabling is typically broken down in what they call categories, category 5, 6, 7, and now 8. This is a version called UTP, unshielded twisted pair. There is no additional grounding or shielding that is wrapped around the twisted pairs inside the cabling. It uses this old gray, and some of them is the blue PVC wrapping there. A lot of this has been they don't allow you to use it anymore in new construction because this old PVC casing here, it when it burns, it lets off noxious gases that kill us human critters. The newer versions of it, the shielded twisted pair, this is the next flavor of it. They have this aluminum shielding inside here. It also includes a common grounding wire, as well as this fiber piece here that when I first saw that, I'm going, boy, that gets in the way. And then another engineer showed me, he's going, watch this. Instead of using a razor to try to trim back the casing on this, where you always cut into the underlying wire, if you just put just a little bitty slice right there in that casing and then use that fiber, you strip that sucker down to wherever you want it to go without cutting in and providing ground out possibilities on any of the other wire. So this is the next version of it, the shielded twisted pair. Now that shielding there gives you additional guarding against what's called EMI, electromagnetic interference. There's also shielding against radio frequency interference, which can interrupt and interfere with the signal going down these as well. In some of the higher quality and higher priced versions of those, in addition to the aluminum wrapping grounding around it, some of the higher ones will have the braided copper, much like coax cable. Pretty expensive, but very well grounded, good protection on EMI and RFI interference. Everything you need to know on the questions you're going to be asked about on your exam is either with the color coding or with this chart right here. Okay. It tells you the category they're talking about, and that typically identifies the number of wires that are being used in that 8-wire cable. Okay. It tells you what the transfer rate is. That is either in megabits per second or gigabits per second. Remember, that's millions of bits per second or billions of bits per second. This will tell you what the maximum distance or length of the cable is with these different designations before you start getting what's referred to as attenuation or weakness of signal. Okay. Now, for the longest time with the Cat 5, 6, and 7 cable, about 100 meters is what you were looking at. And you can run the cable longer than that, but the signal starts getting weaker and weaker and weaker. And then here is the Ethernet standard, which tells you basically the nomenclature of the wire itself. The first part of it tells you that it is either megabits per second or gigabits per second. And then you get into the 10G, 10 gigabits per second, or 25 or 40 gigabits per second. It tells you if you're talking about a basic broadband connection that is just base, or gigabit base, G base, the super high speed connectivity. And the ending character always begins with T, telling me that it is a twisted pair cable. Okay. Now, some of the designation when we start getting into fiber optic cable, that ending character is not a T. It's actually a combination of a couple of different characters. But if you see the designation there and the latter part of it begins with a T, guarantee that is a twisted pair copper cabling that you're talking about. So memorize this chart. Once again, best way I would do it would be with flashcards, and then get somebody that you know and love to help you study this stuff, as well as the color coding that I talked about. And that will answer just about all the questions you need. Now, here are the pin configurations for the cable ends. I talked about the EIA, the TIA, the Electronics Industry Association, and the Telecommunications Industry Alliance. They came out with these guidelines years ago, way back in the dark ages of networking. There were like 3 or 4 different companies all over the world that developed these cables and created them, and they just sort of picked their own color coding. EIA, TIA sort of established the worldwide standard for color coding. And then they also established these two different cable ends here. Now, I will tell you, most of the modernized equipment, the switching equipment, routing equipment, computer systems, etc., you can use, for the most part, now you need to check the specs to make certain, but you can use what's called a straight through cable on all of your connections. And the switching and equipment actually handles the what we will call the crossover. And I'll define that in just a second. The A standard here is this color coding. Pin number 1, green and white striped wire. Pin number 2, solid green wire. Pin number 3, orange and white striped wire. Pin number 4, solid blue. Pin number 5, striped blue and white. Pin number 6, solid orange. Pin number 7, brown and white stripe. Pin number 8, brown solid. You'll notice between the A and the B standards, the blue and the brown wires are the same. It's the transmit and receive wires, the orange and green wires, that are swapped. Okay? That's important here in just a moment. If I am going to be plugging up two different types of equipment, two different pieces of equipment, for instance, a PC computer to a switch or a switch to a router, different types of equipment, I'll use what's called a straight through cable. And I prefer to wire both ends if I'm building the cable with the 568A standard. Okay. So both ends of the cable, same pin configuration here. It's called a straight through cable. If I am hooking up two pieces of equipment that are like, I can wire one computer straight up to another computer and have them network together. A switch to a switch, a router to a router. I will use what's called a crossover cable. I'll wire one end of the connector, the RJ45 connector, with the A standard. I'll wire the other end with the B standard. And you'll notice what it does is I was talking about the transmit and receive pins. It crosses those over. And it simulates a modem in the middle of that connection so that it, transmit, receive, transmit, receive. So it's called a crossover cable. Now, there's a third version of it referred to as a rollover or a console management cable. And I do one end with the 568A standard. Whoop. And on the other end, you just roll over all the wires. 1 goes to 8, 2 goes to 7, 3 goes to 6, 4 goes to 5. Just roll those wires over. And that's used for the plugging into the management console, for instance, in the back of a router or the back of a switch device. So I can plug my PC into that and manage that, log into the management console, make management changes. Called a management console or a rollover cable. Now, most of those devices as well nowadays, you just dial those up on a network connection using their IP address and you log into them over the network connection. But if you're hardwiring to it, all of them have a management console port on the back of those devices. So remember, straight through, if you're hooking up different types of devices, a PC to a switch to a router, a crossover cable if you're hooking up two of the same type of devices, switch to switch, PC to PC, router to router, that kind of thing. And then the rollover cable or management console cable, if you are doing the management on the back of the management port on the back of some of those devices. This is a tool you absolutely got to have in your toolbox. Wire stripper, wire crimper, wire stripper. The one that my youngest son manages a company that they have computer-based systems they install for lighting and insect control and all kinds of stuff. Well, he inherited my toolbox, and he's got a nice toolbox, I tell you. I talked about the punch down tool, punching down the wires into the connectors on the back of a switch device. This is your stripper, your snipper, your wire crimper, all in one. And there's another device, this guy here. This is a device that allows me to put the ends on cable. RJ45 connector ends, RJ11, typically coax cable ends, and some of them even have the crimper where you can attach fiber optic ends on fiber optic cable. There's a punch down tool right there to strip those wires back and punch them down into those Firestone type connectors there. Um, so and I'll tell you too, in your toolbox, don't crimp on your tools. I mean, are use high quality tools, and you'll thank yourself for it later on down the line. Here is a device that allows me to check um, cable, the wires in a cable, end-to-end type of cable testing. It saves an 8-wire cable. It'll test each and every wire, tell you if you've got any blockages, if you got a crimped wire or a broken wire down the line, and most of them will give you, in addition to LED lights that show you the strength of the signaling. That also has audible tones, some of those. And this guy here, the toner probe, I'm gonna have to grab me a new graphic on this new slide for this latest version here. They don't have. It's called a fox and a hound. It's similar to this in that you plug a cable into one end, and then it emits an audible tone down the wire that you can trace through walls and between floors and things like that with the trace unit, the probe unit, toner probe unit. Um, I was hired to do a network closet rewire for a large company downtown Atlanta, and they had 4 different network closets that were separated over 12 floors. About every 3 or 4 floors, they'd have another network closet. I had to get 3 of my employees certified by the elevator company, so it was safety certified, so they could crawl up and down in the elevator shaft because they were tracing wires. I was talking about the cables hanging out in the wiring closet. When I first walked into that place, walked in the first wiring closet, it looked like the spaghetti factory had exploded in there. There are wires hanging out everywhere. Labels? No, no labels. I almost turned down the gig. I'm really glad I didn't because it kept several employees gainfully employed for almost a year, and it ended up buying my house too. So I'm glad I took the gig, but man, it was a hassle. This is called a loop back plug. Notice the orange and green wires. That's the transmit and receive crossover there. You can build these for about 25 cents. The parts store will sell them to you. They'll sell you a bag of, I guess, 3 of them for like 11, $12, something like that. You can get a whole big old bag of these RJ45 clips for a couple of bucks, and then a couple of 4-inch pieces of wire, and it's basically crossing over pins 1 and 3 to 2 and 6. And what it does is it simulates a network connection. So I can plug that into my NIC, and the NIC thinks it's talking over a network. Okay. So I can do that locally. This thing they call a network tabs or a test access point. I can set up and actually monitor and grab network traffic off of the switches. It's more of a passive kind of thing. If I'm just monitoring, not really doing anything with it. But if I am capturing or redirecting those data frames, for instance, to another device where I can do more scrutiny and analysis of the data frames. I was talking about the switches, the managed multi-layer switches. The all of those, because they don't broadcast every data frame on every port anymore, they will set aside what's called a TAP, a test access port, or a mirror port, they call it. So I can have every packet that is introduced into that switch, I can have it a mirror copy of it made. That's the active portion of it. And then send that to another computer system where I can run it through a series of security filters if I wish, and further scrutinize and monitor that traffic sort of offline from the switch, looking for malicious behavior, that kind of thing. There is one version of the twisted pair cabling that is referred to as plenum rated. Plenum rated meaning that it is okay to run it in pretty much close proximity to the air conditioning venting for the HVAC systems. The plenum cabling, that orange cabling that we looked at in that in the wiring closet, that's plenum rated cable. The ends are molded into the cable. It's not crimped on with openings. The PVC coating, it's very specialized. It doesn't burn. It will melt, but it doesn't burn and give off these noxious gases that can kill us. Because oftentimes the networking people now, so as to separate the network cable far enough away from the power cabling, which can generate all kind of interference, oftentimes they'll run the network cabling in very close proximity and sometimes even in the same areas where the HVAC ductworking is. So if it catches on fire, you don't want the old cable noxious fumes going through the HVAC system and delivered to every room. Okay. Also, if you are going to be installing cable, for instance, outside that runs between buildings and so on, the plenum rated cabling is highly suggested because it's much more not weatherproof, but weather resistant. And you always want to run any outside cable inside some type kind of casing, PVC piping casing, something like that, to protect it away from the elements in general. Fiber optic cabling, a little bit different beast than your wired cabling. It typically has a single core right down the middle of it, very, very thin core. And I'm talking about microns, 15 to 20 microns thick, which is, about half the width of a human hair. Much, much longer distances as far as the signaling. It's not electromagnetic. It uses light pulses generated either by very high intensity lasers or very high intensity LEDs. And a lot of the LED, especially for the shorter run stuff now, it comes in a couple of modes called single mode fiber and multi-mode fiber. The single mode is used typically for very long broadcast distances. And we're talking about, kilometers, 20, 30, 40 kilometers as far as the distance on those before the signal starts to attenuate at all. And then the multi-mode, thicker core, and the multi-mode fiber is used usually for short, like robotics and things like that, short run type cable. And because of the thickness of the core, they can broadcast multiple light frequency signals on the same core. So multiple signals simultaneously there. Have there's about five connector types. There's one called a straight tip or a standard tip. There's one called the standard connect and local connect. These are the standard connect and the local connect. This one also used to be called Lucent Connect. That was the company that created it. But fiber optic cabling, just like copper cabling, it can communicate in both directions, but if it's only a single cable, it can only communicate one direction at a time. So the switching equipment needs to handle turning around and, broadcast, receive, broadcast, receive. Along those lines, we are very common now seeing twin fiber optic cables run between switches, for instance, or routers, so that it can do that duplex communication, full duplex simultaneous communication. The fiber optic is beginning to replace a lot of your copper cabling. This old bad boy here, coax cabling. Standard coax. You've got two flavors of it. Basically, you got one version called a thick net, which is about a ½ inch diameter. You got the rubber plastic composite coating, weatherproofing. You have the braided copper shielding inside. That plays dual purpose. It gives you strength. It also casts off any type of electromagnetic interference, and it acts as the grounding function of the cabling. And then usually you have this sticky aluminum insulation on the inside of it, more EMI type protection. Usually you'll have the rubber plastic composite core that surrounds the main hot lead there. And it's copper cabling, electromagnetic cabling. You also have two different types of ends. You have the F type connector, which is one that you screw into the connector. And then there's another version of it. Military cats are familiar with this. You have another version of it called BNC, bayonet Neil Consulman. It's a push twist and you're connected. So very rapid setup and teardown, especially if you're setting up like field networks. And the cable itself is only about a quarter of an inch as far as the diameter. Same wrapping type, same configuration, only thinner. They call it thin net, and it uses that BNC type connector there. So that's a pretty good overview of your different network cable types. You have the copper cabling, either with the 8-wire twisted pair, the 4-wire telephone cabling. The RJ45 is the 8-wire Ethernet cabling ends. The RJ11 is the telephone cable end. And then you have your coax cable, copper cabling. And then you have your fiber optic cabling, which is not an electromagnetic kind of thing at all. Then we have our wireless networks. This is where we start getting into the 802.11 IEEE standard here. The wired, remember, is 802.3. The wireless 802.11 is the standard and framework there. It all begins with some type of access point, a wireless access point. The access point has its own what they call the SSID, the service set identifier. That is the name of that wireless access point. The wireless access point also has its own unique MAC address. Okay? And same structure as your network interface card. This serves as a hub, as it were, to multiple wireless appliances that can talk to it. According to the 802.11 standards, dictates the frequencies the wireless frequencies that are used to communicate with this thing. The standard frequencies on these used to be limited to 2.4 gigahertz frequency range and 5 gigahertz frequency range. Now with the new modernized systems, like our home control systems, the Alexas, the Siris, the voice control systems, other voice control systems that we have in our homes, many of those are using these mesh network communique and using the 6 gigahertz frequency band as well. The very first version of these, when it first came out, used 5 gigahertz frequencies only. It was, as we compare it today, very slow, but for the time, it was screaming fast, 54 megabits per second. And it utilized a dynamic they call DFS frequency selection range, DFS, dynamic frequency selection. There were 23 non-overlapping channels that were available in that frequency range. And the issue that they had with this thing when they first came out, about the same time when these were introduced, also some of your telephone companies had just introduced some of their wireless telephone kits that also operated in somewhere in that 5 gigahertz frequency range. So we had a conflict there. Well, almost immediately within months after this release, they released 802.11b, which used the much more, not really powerful, but much more penetrating, as it were, 2.4 gig frequency band. And it utilized a couple of different modulation schemes here. Used the dynamic selection scheme and one called the orthogonal frequency modulation, or orthogonal frequency dynamic modulation, I guess. But the problem with the very first version of this 802.11b was that it propagated much better, like through solid walls, than the 5 gigahertz did, but it had limitations. Of the 14 available channels in that frequency range, the FCC only allowed us in North America to use the first 11. And you had a 5-channel overlap of the signal would bleed into 5 channels deep. So you had to separate the channels. Plus, the biggest deal was that it cut the speed down from 54 megabits per second to 11 megabits per second. So that for the time was still pretty fast, but it was crawling, absolutely crawling. They later on released a version of it called 802.11g, which did both, supported both the 2.4 gigahertz and the 5 gigahertz frequency band in a singular device. That's the overlap I was talking about. You had to, if you're using like three of these things in the same company, you had to separate the channels there, channel 1, channel 6, channel 11, or you get that channel bleed over it. It will cause interference, no doubt about it. Okay. So of the other three channels, 12, 13, 14, those are, they can't use them in North America. They use those in other parts of the world. Japan, for instance, uses all those. Here we started getting into really high speed wireless access points. We started getting into 802.11n, dual band also, 2.4 gigahertz, 5 gigahertz. And it utilized a pretty clever function. It was called MIMO, multiple input, multiple output. And those devices usually had multiple antenna, sometimes four antenna on the outside of the device. And it allowed me a clever little thing called channel bonding. So I could bond together multiple channels, two channels, and increase the speed. Okay. So pretty interesting the way that it came about. These things, some of them were beginning to push about a half gigabyte speed, 600 megabyte speed there, megabits per second, not megabytes. Then we started getting into the real high speed bad boys here. The one that I have in my home network here is this guy right here, 802.11ax. It supports all three of the band ranges, 2.4 gigahertz, 5 gigahertz, 6 gigahertz for the mesh network, the Alexas of the world, that kind of thing. It also utilizes now the orthogonal frequency modulation routine, and it's just the way that it modulates the signals, the wireless signals. Um, this thing is very fast, or has capability of being very fast. It's all dependent upon the speed of the pipe that you have running into it. Luckily, in both of my office locations, I've got the very high speed fiber optic cable, so it's screaming fast. Um, and like I say, it's multi-band support. So I've got part of the systems in my home network here, the ones that are in real close proximity in the same room, or one room separated from the access point. They communicate 5 gigahertz, very fast, very high speed. The ones that are hardwired or communicating through walls, that kind of thing, are using the 2.4 frequency range. And then, of course, the mesh network things, the Alexa components and some of the security components communicate with the 6 gigahertz frequency range. So it's very high speed, very powerful, really, really good kit. I like it a lot. And it uses, again, sort of a combination of the DFS and the orthogonal frequency modulation functions there, according to the different types of frequencies that you're using there. And again, very high speed, very clear communication. Now, this is the next thing that's coming down the pipe. Very high speed, 46 gigabits per second. That's some screaming stuff there. Wi-Fi 7, they're touting that. Or 802.11be is the designation from the IEEE organization. Also will support, or is supporting, they've got it in tests all over the place now, supporting 2.4 gigahertz, 5 gigahertz, and the 6 gigahertz net mesh network functionality. But I'm talking about screaming fast speeds. We're seeing those already set up and being utilized in large data centers, for instance, cloud-based storage data centers and communication between data centers as well. So pretty good stuff there. Now, if you are installing a wireless network, a wireless local area network, a couple of things you want to be concerned with. The placement of the wireless access point in relation to all of the endpoints that need to communicate with it. Also, if you are having the devices that are communicating, in the same room or in the same general area, well, 5 gigahertz is going to be your choice because it's almost direct line of sight kind of stuff and screaming fast. Plus, you have the 23 non-overlapping data channels, and the 5 gigahertz systems can be set up to automatically choose a data channel. If it's one that's transmitting on gets a little bit noisy, it can automatically switch to a different channel for communicating. Now, if you have systems that need to communicate through a couple of walls, well, 2.4 is your better choice because it propagates better through solids than the 5 gigahertz does. Okay. Also, you want to make sure that you don't overload a particular wireless access point with too many devices. Because understand, all of the devices are sharing that bandwidth. Okay. So you have to make sure that you configure that properly. On every one of the appliances, there is a management console. Once again, from a security perspective, you want to make certain that you lock this sucker down and secure the access to the management console. Give you guys a link to a website now you should always be aware of. This is called routerpasswords.com. This is published out there on the worldwide interweb. Every administrative level user ID and password for all of your routers is listed on this website. Okay. You can just choose the router here. Let's see. Let's check one. What we're going to let's do. I don't know. We'll do Cisco. Cisco, I think, has got several different models there. There's all the passwords for all the different models of the Cisco routers posted right online. Okay. The bad guys know how to find this. Okay. So make certain that whomever is setting up your wireless environment and all of your router devices, go into the management console and change that stuff. Set up encryption algorithms. Kaylee, you were asking about encryption earlier. Well, you can encrypt data flowing back and forth between the wireless connections too. Set up a good, strong security environment. We always recommend at the bare minimum Wi-Fi protected access version 3, level 3. Very secure, and you decide what the passcode is going to be. And you have to share that with all the users going to be logging into this thing. The strength of the signal, if you have anything that is standing in the way of that signal strength, you also need to be aware of that. I'm going to give you another link here. There's an organization known as CoolSoft. They have, no, not Keysoft, CoolSoft, or it's KEWL, I guess. They publish a piece of software. It's called a Wi-Fi analyzer. All right, where are you now? All these crazy different websites here popping up. Well, where's my link now? There she blows. That's it. Yeah. Oh, it's cool.com. They changed the website link there. I see. And here is the Wi-Fi analyzer link right here. It is free. It's a great little tool. I have it running on my Android phone and my Android tablet. It doesn't work on iOS right now, but I use it to basically do a walkabout in my network environment, and it will show me where all of the Wi-Fi signals are. It will show me the names, the channel they're broadcasting, the strength, if I have any overlapping channels, things like that. And you can't be it free no matter how hard you try. Now, once again, it only works on Android devices. But grab it, download it, use it, and you just walk around in your environment, and it will show you what the signal strength on all the channels that are broadcasting are. Here's another version of this Insider, they call it, INSSIDER. Same thing. It tells you what the name of the device is over here. Tells you what the strength of the signal is, the channel that they're operating on here. If it's secure or not, down here on the graph, it shows you've got overlapping. It will show you signals on all three of the bands now, 2.4 gigahertz, 5 gigahertz, 6 gigahertz. So it will assist you in sort of fine tuning the signaling on all your Wi-Fi devices. It'll also help you to paint what's called a heat map. So you can see if you're getting any interference from other signals, things like that, and just sort of fine tune your wireless network there as well. Okay. Now, there are other implementations of wireless networks as well. Some of them are antenna oriented, antennas posted on buildings, long range signaling, very high powered broadcast antenna. There's, I don't know, two or three different types of antenna on these things that, point to point communication. You see them driving down the interstate, the cellular towers, same sort of high speed antenna transmission of these signals as well, but on a scale down, closer proximity. There was a couple of companies that tried their best. One of them right here locally for us. We live at the base of a little mountain here up in northeast Georgia, and well, North Georgia and northeast part of the county I live in. And there's a little mountain up here over behind our house. Well, it's a foothill. Okay, it's not a mountain. But this company came in and set up their towers on top of the mountain there, and they were trying to implement these complete wireless network internet connections. And we were one of their beta testers. We had their little unit that we brought in. We plugged. They gave us the modems, I guess, the Wi-Fi access points that we plugged into just power outlets throughout the home. And while the thing was working, it worked pretty well. But I don't know if they managed themselves out of business, whatever, but they went out of business. And they never did get it fine tuned to where it provided constant good service. Now we're going to start seeing some wireless network adopted, and we already have. All of your cellular companies now are beginning to switch people over to just use their wireless hotspots, their Wi-Fi hotspots, and that's their internet connection. We also now are beginning to see quite a movement towards users using their cellular connectivity as their internet connection as well. Even just a small hotspot running on their phone, for instance. So we're going to see much more of that, and we're going to start seeing a lot of people are jumping ship over to like they call it the LEO, the low Earth orbit satellite grids, like Elon Musk's satellite grid. Pretty cool connectivity there. Now, currently it's a little bit expensive, but they are the price is beginning to come on down on some of that connectivity as well. In addition to the wireless fidelity, the Wi-Fi connectivity, we're also using other wireless connections here as well. We talked yesterday about Bluetooth. Bluetooth also operates in a 2.4 gigahertz frequency realm. It's relatively close proximity, usually no further than about 10 meters, 28 and a half feet or so. And then you start getting signal attenuation, or it just completely drops the signal. Bluetooth is reliant upon a pairing situation where you pair between the Bluetooth device and whatever it is, headphones, speakers, other mobile phones and computers, things like that. I have this printer I have in my office up here. I can print to it directly with Bluetooth or Wi-Fi direct, either one. We also have these near field communications is very close proximity. That is in place for like your tap to pay functions, the tap to pay software that we run on mobile phones. Just tap it over on a device and it transmits data. That's real close, about 9-10 centimeters proximity there. And then the radio frequency, the RFID trackers. Walmart, for instance, was the first company in North America that started including the little RFID tags on their merchandise and the readers at the door, that sound the alarm if people try to sneak out without paying for a product here. But it all over the airwaves, you see. Bluetooth is being used a lot. I was telling you about my wireless mouse and my wireless keyboard and the Bluetooth communication with the printer there. A lot. And again, most of those are pretty close proximity, less than about 30 feet for the most part there. Okay. All right, my friends, what we want to do right now And for those of you that are listening in on the worldwide interweb, you won't be able to do this, but I am going to set up a timer. The students now will be going through a quiz exercise here on our learning platform. I want you all to navigate on over here to your quiz example here, a lesson review here. And when we get back from this, there's an activity that we're going to be doing here as a team. I'll step you guys through that. But right now, I want you to jump over here and go through this module quiz. Of course, making me log back in. All right. The module quiz is 20 questions only. I'm going to set you guys timer up for 30 minutes. Now you folks, if you're keyed in through the through YouTube and the internet, you're welcome to hang with us. I'll be firing the recording back up after this. Well, I'm going to keep the timer up during the break there. So you just hang with us, and we'll pick back up with some more lecture here in just a little while. So let's go down to your module 5 in the outline here and do your module quiz. We always do this. We have the students do their module quiz. They post their scores in the chat box, and they are proud of those scores. They own those scores. Okay. And we encourage everybody to repeat these quizzes multiple times because the repetition there is an excellent teaching aid, no doubt. So you all post your scores, and then we'll take a quick break. And set the timer up here. Boom. Give you guys 30 minutes on your timer. That ought to give you plenty of time to do the quiz, to post your scores, and to grab that quick latrine or coffee break. So, any questions, either of you, before we go ahead and pull the trigger on this timer here?
Not from me.
All righty, we'll dive in on it. Have a good time, and I can't wait to see those scores. I'll see you guys back here shortly.